Adhesives are commonly used in everyday life for all kinds of repairs and have been widely used by many industries over the years. The adhesive market was valued at $52.5 billion in 2017. Its increasing demand in automotive, construction, packaging, furniture, and footwear applications are the factors that drive annual growth. Adhesives are essential but can cause environmental damage and are detrimental to workers' human health and communities. An industry that is close to home is the footwear industry. It is unimaginable to think about life before shoes were invented. Footwear is part of one of the largest and most important industries worldwide, fashion. An industry that, according to the Worldwide Fund for Nature organization, generates 1.7 billion tons of carbon dioxide annually, of which 1/5 are produced by the footwear industry. It is estimated that an average person buys around 7.8 pairs of shoes per year. To satisfy the demand, about 23 million shoes are produced yearly, generating large amounts of CO2, equivalent to 300 million cars emissions. But what is generating this large and growing carbon footprint? One shoe is generally made of a heel, insole, midsole, upper layer, and outer sole are made of synthetic materials coming from fossil fuels, coal, and oil. Imagine this. A shoe can be made up of 65 parts produced in many different factories, allowing for an inexpensive production. The separate parts are transported to a single assembly site for cutting, pouring, casting, baking, cooling, and gluing processes. It is estimated that 20% of the carbon footprint produced by a pair of shoes comes from material composition, 60% from manufacturing, and 20% from the assembly, leading to 25 kilograms of carbon dioxide for its production. Also, industry workers are exposed to substances such as vapors produced by traditional toxic glues, generating diseases, causing irreversible damage to the body, and can even lead to death. Shoemaker's paralysis, a neuropathy caused by N-hexane poisoning, is present in most glues and solvents, a common condition within this industry, causing lower extremities paralysis. Solvent poisoning can cause anemia and leukemia, and contact with substances containing polychloroprene causes dermatitis. Our challenge starts with what's behind a pair of shoes. Before reaching your feet, shoes are usually designed by a brand, distributed by a supplier, and manufactured mostly by subcontractors. Human hands assemble its parts, contributing to a fast consumption model found at the heart of the footwear industry. However, the shoe manufacturer in marginalized communities usually lack job security, and gluing can become an occupational hazard. Most commonly used adhesives are rubber-based diluted in organic heptane and hexane solvents. Rubber provides adhesive properties, while solvents facilitate adhesive distribution on all types of substrates. The bonding process consolidates when evaporated, and it works on any type of surface, requiring the use of a brush. However, it has a high environmental cost because of the inherent toxic gases that are emitted into the atmosphere, and it takes approximately 100 years for rubber to biodegrade. Then, there are water-based polyurethane adhesives that use a heating device for its evaporation and a cold one for proper bonding of the shoe. Unlike solvents, polyurethane is a specialized glue, so its components vary according to the bonding surface. Although the use of water reduces its carbon footprint, an oil-derived material is used which can take between 20 to 30 years to biodegrade. Finally, sustainable adhesives are made up of repulpable, renewable, recyclable, biodegradable, and compostable adhesives. However, each one has a limited range of action, since it only works on specific substrates, and its adhesion force is not the same as the previous two. The need for a bio-designed, healthier adhesive that meets the demands of the industry is fundamental. Introducing Vivifica, a bio-based, environmentally friendly glue alternative for the footwear industry. inspired by the adhesive qualities of the Colobacter crescentus bacterium. To colonize surfaces, this aquatic bacterium expels its flagellum and synthesizes a holdfast in the same pole. This way, it adheres to the surface to subsequently initiate cell division, where the process is repeated until a biofilm composed of stalk cells builds. The intrinsic adhesive force in the bacterium is a powerful natural alternative. The holdfast is a polysaccharides extracellular matrix composed mainly of N-acetylglucosamine and other sugars such as mannose, glucose, and xylose. These compounds give it mechanical properties similar to an elastic gel, and an adhesion force of approximately 68 Newton per millimeter square. For you to imagine the adhesive strength, rubber-based adhesives have a strength of 2 Newton per millimeter square, 34 times stronger. It adheres to both abiotic and biotic hydrophobic surfaces, and according to studies, to a wide range of substrates such as glass, mica, and graphite. Its dry fixing height is approximately 1/3 to the fixing in humidity, thus demonstrating an affinity in different types of environments. Its properties supply a powerful, efficient, and functional alternative. Generating a bacterial culture requires precision and resources, thus we are using synthetic biology, targeting the demands of the adhesive industry. This process is made up of 3 steps: genetic information, growth of genetically modified bacteria, and purification. In the first step, the gene responsible for secreting the holdfast is identified and cloned into a plasmid. Then it's introduced into the biosynthetic agent through an electroporation process. We chose E. coli bacterium for its well-characterized genome, well-understood physiology, and a well-developed set of synthetic biology tools. Once we have the modified bacteria, the process of growth and production begins. We incorporate a bioreactor and a culture medium in the first step. To synthesize the holdfast glue, the bacteria must be fed on peptone yeast as the medium. At the end of the production process, the purification process begins. The substance is filtered, separating the vesicles that the polysaccharides matrix contains from the bacteria. This is how we obtain our holdfast glue. Its universal bonding property does not emit toxic gases such as the polyurethane adhesives, and it's biodegradable, similar to sustainable adhesives. To start, we would work for the small footwear manufacturer. We designed a device that responds both to the chemical and physical properties of the holdfast glue and to the tools that are currently used in this environment. Vivifica is made of a hydrophilic PET, preventing the substance from sticking to its walls, a lid of the same material that works as a support of the device while it's not in use, and a roll-on mechanism for adequate gel dispersion. Finally, its shape is inspired by a brush's morphology, obtaining a product gesture similar to the current one. The bottom of the device rotates, causing the grip area and application angle to change for greater comfort when using it. Therefore, the device allows a uniform layer when gluing the sole. Its rechargeable cartridges dispense the bioadhesive, prolonging lifetime. For safe use of the product, factory workers must wear gloves, avoiding contact with the substance, and in case of a spill or misuse, it can be removed by using substances with a basic pH. In the long term, we envision Vivifica as a glue alternative that can be scaled to other industries, a contribution to the dream of building a carbon-neutral world. We want to be part of the new paradigm where our negative impact on humans and the environment is diminished in the manufacturing stage. Because of the pandemic, we know more than ever that we're bound together in one world. Vivifica, a bio-based universal adhesive. Vivifica, the holdfast glue.